Okay, everyone. I know it's not a long lunch break. I know. we're totally aware of this. So what we arranged that the food will be, at least the hot food will be out there for another 20 minutes, and also the dessert will stay in the back of the room, and you can grab one when you like. We would like to continue with our sessions, and it would be great if you just take your plates and sit down and eat while you're listening. Then you cannot talk. That's even better. And try to eat a bit, not too loud. But we have a nice program prepared for the afternoon session. And now I'm not going to share the session actually, but Benoit will share the session and talk about the weather-extreme digital twins and all the applications. So please.
Thanks. I will give 1 or 2 minutes for people to join their seats. Everyone, please, could you join your seats? So we'll kick this session on the Extreme Digital Twin, which is one of the first 2 high-priority digital twins developed at ECMWF. And I will present the global component of the Extremes Digital Twin on behalf of my colleagues at ECMWF. So to put it in a wider context, the Extremes DT is made of several components, a global component using IFS NEMO, which will simulate extreme weather events worldwide 4 days ahead, and which is running at a resolution of 4 kilometers. Then the detection triggering algorithm is scanning the IFS ensemble to detect the likelihood and the severity of extreme weather in Europe, and will issue a priority index. The regional simulations can be triggered on demand, and they enable a zoom-in capability with a flexible domain 2 days ahead, running at sub-kilometer scale. And finally, impact sector models will provide sectoral information, which is more directly integrated to, directly related to impacts, and they will be integrated both in the global component and in the regional component of the DT. So I will concentrate on the global simulation in this presentation, and then after me, Christophe will present the regional component. But what makes the Extremes DT a digital twin and fundamentally different from all the tools that we have currently? First, we are improving the quality of the simulations by increasing their resolution. We are operationalizing the on-demand capability of regional simulations, and we are enhancing the interactivity of those simulations for impact sector models, giving them the possibility of a direct coupling with the digital twins. So for the global DT, the main added value is the increased resolution, and that's what will bring better quality information to users. And to demonstrate that, we have been comparing the global digital twin to the operational forecast produced at ECMWF using a resolution of 9 kilometers. And we have seen improvement in the representation of tropical cyclones and medicanes. And you see here the example of the tropical cyclone Beryl, where the DestinE forecast produced an intensity twice as strong as the operational forecast of ECMWF, in good agreement with the observations. We have seen an increase of the intensity of orographic precipitation, and the global DT benefits from the steeper slopes of the orography. We have seen more penetration of wind gust over land, again in better agreement with the observations. We have also seen an improvement of 2-meter temperature prediction, especially in regions of complex orography and during strong boundary layer inversions. But you will hear more about that in the presentation given by Natalie and Esti later on. If we want to deliver a better quality information to users, we also need to work on the physics of the IFS. And one of the main challenges for us is the representation of deep convection. You see, we are using currently a standard convection scheme of the IFS, and you see that we produce much more weak precipitation in purple compared to the observations I merge. And we have also some undesirable features with those wavy pattern like fish bones. The Climate DT has pursued another strategy, which is to rely less on the convection scheme. They have reduced the cloud-based mass flux. That's what you see in C. They have more round-shaped mesoscale convective systems, but the disadvantage is to increase even more weaker precipitation. And many groups doing kilometer scale modeling rely on explicit deep convection, where they switch off the deep convection scheme. In our case, it produces two narrow mesoscale convective systems and two intense as well. So we are trying to improve the representation of deep convection, but this is a challenge, and we are not there yet. We have also been working on increasing the resolution of the orography, relying on higher resolution source data sets, the Copernicus GLOW 30 DEM. We have integrated a new prognostic TK scheme, which will allow to represent better regime transitions in the boundary layer. And finally, we are working on producing an ensemble at kilometer scale with 10 members to address uncertainty. We have integrated two impact sector models directly in the global digital twin, and the motivation for that is in the long term to represent their impact on the larger scale Earth system. So we have integrated Camaflood to model river discharge. We have identified a challenge there, which is that Camaflood is mainly forced by the model runoff, which is sensitive to resolution in the model, and as a result, we produce weaker river discharge in the extremes DT in blue compared to the operational forecast in red. So we are working on improving that. We have also integrated a flexible prognostic aerosol scheme, which allow to model explicitly and prognostically a few aerosol species, like dust, black carbon, and organic matter, while keeping all the others climatological. So that reduces a lot the cost of the simulation of aerosols compared to having all aerosol species prognostic. In the first phase of the project, two use cases have integrated their application directly in the global DT. DeltaRes integrated the Sphinx model for compound flooding. They had 5 pilot regions around the world. And you see here the case of the tropical cyclone Fakir in La Réunion, which in that case really benefited from the increased resolution of the input data from the global DT because of the strong orographic component of precipitation. But in some cases, some other cases, they told us that they really needed some uncertainty quantification, which we did not provide. They also told us that having high-resolution bathymetry for coastal flooding was as important as high-resolution NWP data. So those ancillary information also are crucial and should be delivered by DestinE. The Forschung Zentrum Jülich integrated the URAD-IM model for trace cases and aerosol dispersion. They tested several scenarios to restrict emissions due to industrial activity and traffic. And in their case, the main limitation maybe was this light precipitation bias that I mentioned before, which is quite detrimental for air quality because it generates too much deposition of aerosols. You will see later on the presentation by Kunyan on flood prediction by DeltaRes. We have also tested the integration of another digital twin, Glory, in the global DT to demonstrate the interoperability of those digital twins. So DestinE is providing lateral boundary conditions for the atmosphere and ocean component of ICON, running both at 2 kilometers. The data have been extracted by Polytope. And then those two components are coupled by the YAC coupler. So I think we have demonstrated here that the compatibility of the data format between the digital twins, and this digital twin has been deployed on the EuroHPC Leonardo. And finally, if you want to get started with the Extremes DT, you should know that we provide on the DestinE service platform access to the global DT data for the last 15 days with an upgraded access. So if you want more information about the Extremes DT, you can check this page on the DestinE ECMWF website on the left. And if you want some example Jupyter notebooks on how to retrieve global DT data with the API Polytope, you can check this webpage on the right. So with that, I would like to thank you all, and I would like to pass the floor to the next speaker, Christophe.
Thanks, Benoit. Is there one quick question for Benoit, maybe? That's immediately relevant. Okay, then go ahead.
Thank you. Okay, it's a pleasure for me to present you the development status and the future directions of the regional on-demand Extremes Digital Twin. My name is Christoph Wittmann. I'm working here in Vienna at GS for Austria, the National Austrian Weather Service. And I'm giving this presentation on behalf of the Extremes Digital Twin team. This is really a huge team. Almost 30 partner institutes taking part in this project and cooperating closely together with the Destination Earth team from ECMWF. I have just a few minutes to show you what we do and to show you our progress. This is quite a challenge, but after these minutes, I want you to know what are our goals, what are the components of our workflow, and what does it look like at the moment, and where are we going to? And then I would like to show you just a few cases how we are at the moment piloting these extreme events. So what about our goals? So we want to develop a high configurable digital twin, really to simulate past, present, and probably also future extreme events. And we want to make use as much as possible from the EuroHPC capabilities. So you just heard about the global DT, now it's about the regional one, running on the heterometric scale resolutions over Europe. So a clear goal is also to connect these weather twins to the impact sector models and modules. So this is really a high priority goal for us, and this is done within a single workflow. So the information we are creating finally, this should be for the national authorities to create, to act as a supporting information for the national authorities, for the impact sectors, and so on. It should complement all the information which is available now already. And finally, this is not done now at the moment, but this is an option for the future. We want to allow exploitation of the so-called what-if scenarios. Yeah, this slide now schematically illustrates how the workflow is currently looking like. So we are talking about the on-demand regional digital twin. So that means we are not running daily. So we need to know when and where to run our system. So that's why we need a detection and a triggering module. So this is based at the moment on the global forecast of the ECMWF ensemble system. So there is a system detecting coming extreme events, configuring, creating configurations for our system, and then we do this in a semi-automatic way at the moment. There is a team daily looking on the results of this triggering information, and then deciding whether and where to run our digital twins. So once the decision is done, then the weather twins, so the high-resolution numerical models are running, coupled to the global digital twin. And then next step, then it's the impact modules and models who are entering the chain and post-processing and so on until it finally arrives at the data bridge in the future. So at the moment, we are developing and piloting this on the ATOS ECMWF HPC and testing it already step by step on the Euro HPC. So triggering capability is a really important part of our work. So at the moment, the status is that we apply our triggering algorithms on purely meteorological parameters. So that means we are scanning the global forecasts from ECMWF, identifying regions where we have extremes based on precipitation, wind, temperature, and parameters like that. Then we have this detection, which is based on thresholds, where you compare the forecast to a climatological information. And then finally, our system is giving priorities for regions in Europe where we can run our DTs. So, and we are now in the step of extending these capabilities to impact sector-based triggering. So that means we want to include ramping events or storm surge or air quality measures to be included now within the next steps into these triggering capabilities. Once we know where to run, we start our weather digital twin, and for us that means that we are running our numerical weather prediction models on resolutions around 500 to 750 meters. So within the ACCOR and WP consortium, we have different choices for models, and depending on the region where the extreme event is anticipated, then we decide which model configuration is run. Added to that, it was already mentioned, the topic uncertainty. This is really a really important part of our project work, because we all know that weather models are not perfect. Digital twins are not perfect, so there is uncertainty inside, and that's why a major part of the project is dealing with the uncertainty estimation. There are different approaches to do that, ranging from post-processing to the classical ensembles using the weather models itself, and then also, of course, the AI-based methodologies, which are part of the project, so the data-driven models, which also help us to include uncertainty information into our workflow chain. So this is currently developing throughout the project. So most of them are now in a pre-operational stage, ready to be now step by step included into the workflow, which we are piloting on a daily basis. Yeah, and once the DT weather is done, then the job is then for the impact sector models and modules. There's no time now to go into details for all of these models and modules, unfortunately. But this slide just illustrates now which sectors we are currently dealing with and where we are applying impact sector models and modules, which we step by step want to include also into the workflow. In the current piloting phase, for example, the floods, the hydrology modules are already inside, and next are already waiting to be included. So for the impact sectors, we are mainly developing and piloting at the moment on past cases. So this slide just shows an example. So just we were testing on flood events, on frost events, solar eclipse events, and so on. So this is a variety of events we investigated and used to develop and co-design our systems. But a major driver also for us is for sure the present cases, so the actual weather. So this is for sure a main motivation for us, for our developing, and just ending up now with two examples, how this can support, let's say, the daily work, for example, of a National Met Service, where it's about doing warnings, providing information for in critical situations. So we are now piloting at the moment these digital twins, this on-demand. To give you an idea, in 25 we almost reached up to now 200 runs, which were run in near real-time test mode. So and these were mainly warning situations which were covered, and we included also forecasters from Met Service who help us in piloting this and help in this iterative process in developing it. And another example where there is a use case for that, just from last weekend, I don't know, just nearby this area, there was a big event taking place, the Danube Island Music Festival, where many people come together. And fortunately, the weather was really fine, but if an event like that comes along with a critical weather situation, then this can be really critical. So we are also piloting with forecasters events like that to see and test our on-demand system and to iterate this process to make it more useful and help us to be uptaken. So these are two examples of how we piloting present cases, and with that I'm coming to my summary. So we have the regional extremes DT to support the national authorities. That's the plan, to support the impact sectors in the decision process. The workflow is really modular, flexible, and configurable. That's really a highlight. And at the moment, we are demonstrating or piloting it on present and past cases, and probably we extend it to the future in future cases in the next phases. There's a growing number of impact sector models and modules which are coming part of this workflow now. And finally, this DT weather data, there are now first test data sets available on the data bridge, which can then be piloted and tested. So this is just right happening now. Yeah, and with that, I say thank you and happy to receive questions.
Yes, thanks, Christoph. Are there any questions for Christoph? Yes, please. Please, can you go over to the microphone?
Thanks for the nice presentation. If we look at the workflow complexity and a little bit into the future, what computational intensity or capability you envision that? Is it like when you expect the workflow complexity to increase, do you mean more computational capability in terms of capacity, or support for better modalities is necessary? So how do you envision a future, especially looking at such a workflows?
Not sure if I fully got it, but yeah, of course this workflow in the future, when all these components come along, they need these resources, they need these capabilities to be done. But that's why we are targeting on facilities like Euro HPCs, where you have these capabilities to include all these modules and models into the system. Yes, but of course that's a challenge. That's a big challenge, and that's what we are facing now, to make this system also very efficient in what they do. This is a bit in contrast to what high resolution demands. So, but this is needs to be balanced. But it's a big challenge. But there are the capabilities to do that.
Okay, thanks, Christoph. One short one, and then we have to move on. But I do want to say that we do have a discussion session at the end of this, so you memorize your question.
So, is yes or no?
One quick one.
Okay, thank you. Sorry. Can you provide us the reasoning behind feeding your model with forecasts and not with actual measurements, for instance, because detecting extreme events with forecasts, it's challenging. So why not using external data sets, observations?
You mean now for the triggering?
Yes.
Yeah. No, the purpose, what we do now is, so we want to have the triggering for events that take place 1, 2, 3 days in advance. So that's why we rely on the forecasts, on ensemble forecast, probability forecast, to see already in advance when we want to trigger it. So that's the thought behind. If it's about, if that would be a nowcasting system, let's say where it's about predicting the next 1-2 hours, then of course you would much more rely the triggering on observations.
Thanks a lot, Christophe. We have now Nathalie Toyos and Sibalis Gascon talking about improving the simulation of extreme weather in Europe with the Extremes DT.
You have to escape and then choose your talk.
Here. Okay, good afternoon, everyone. So here it will be a common presentation between Natalie from KNMI, who works in the regional Extremes Digital Twin, and Sibalis Gascon, who is me, and I work in ECNWF in the Extremes Global DT. So here this slide was presented by Christophe, and you can see all the contributions that work in the Extremes DT. But probably many of you ask, okay, so we have the global DT extremes and the regional DT extremes, but what is the added value of each one? How we can use them? So the best way to do this, or to answer to this question, is to test different case studies. So we have been testing many case studies in at least 2 years, in the last 2 years, as soon as we have the models developed, fully developed. And you can see here the set of case studies, just some sample of the case studies we evaluated. Many of them we evaluated together to understand what is the added value of each one.
All right, so if we zoom in a little bit in some of these case studies, so this is an example of extreme precipitation, and this was triggered, you can see here, in the south of France and north of Spain. And what you can see is the observations here from European radar data, and below is the global DT. Which shows that it captures some of this precipitation. But then if we zoom into this with a regional on-demand component, we can see that it resolves even more of the extremes, and you can see more better representation of the actual structure of the convection. So it's more structured. And then another precipitation case that we see is this was detected over Italy. So below here you can see the observations from SYNOP stations, and here's the operational IFS, so the high-res 9 kilometers. Then if you go more towards the right, you can see you're adding resolution, so you're zooming in first with the global DT. At 4.5 kilometers, you can see that you're starting to resolve more of the precipitation. But then if you zoom into with this regional on-demand component at 500 meters, you're really starting to resolve more of the extremes and more of the local extremes as well. It might be overdoing it a little bit, but then it's also a question of what you actually observe. So.
Thank you, Natalie. So, okay, nice case studies, we saw the added value, but sometimes it's challenging to evaluate these case studies. And this is one clear example that, for example, it was a extreme wind event. We have strong winds in Corsica and Sardinia. And what happened here is that you can see the increased intensity of these strong winds from the operational IFS 9 kilometers to the global DT 4 kilometers to the regional on-demand 500 kilometers. But this is true. How we can check that? So as you can see, the SYNOP stations coverage is very limited. So even if we see some potential added value, we cannot confirm because we have sometimes lack of observations. This is something we have to work more because without observations, we cannot evaluate the details. But of course, we don't want only case studies. We want to evaluate with proper verification scores. And then for that, we need longer databases. So we were lucky that we managed to have at least 1 year of data in the global DT, and we created these scorecards for extremes that we call scorecards for extremes, because in a general view, you can see for different conditions what is added value over the global DT over the operational IFS 9 kilometers. And this is for 24-hour precipitation. What we did is to calculate the equitable threat score for each condition. And we did the difference of this equitable threat score, which is a verification score. And we used just the 99th percentile of each condition to detect the extremes. What this gives to the user is the added value and also if it's statistically significant. So for example, the square, the black bold squares, means that it's statistically significant. And then the blue colors is that we have some improvement. Indeed, I put the percentages with keep low because obviously it's difficult to improve the model so much. But what we can see is that for mountainous areas, the global DT provides some added value in general. When the flat areas is an average, it's like a bit mixed results. And especially, we provide added value with large-scale precipitation in winter for the mountains. And finally, Benoit mentioned about the complications we have with the convective events. And clearly, you can see these red colors in complex orographic areas when it's summer and autumn, when the convective activity happens. And this is a much nicer scorecards, I would say, is for 10-meter wind speed. And we can see that, in general, for Europe, we provide added value with the global DT for all the type of conditions. But it's not statistically significant in all of them. It's only for the mountainous areas. The percentage you have to see that are quite low, between 2 and 3%. But to improve a model, 2 and 3% is quite a lot.
Okay, so what Esty nicely showed before is that you see added value, especially for wind speed, with going to the global DT. And we see we add even more benefits when we go to the regional on-demand. So this is just, and we've evaluated this also for a longer term. So this is based on, this is the root mean square error and the bias based on 1 month of these 500-meter simulations. And we can see the global DT here is in red, and then we have 2 configurations of the on-demand system in yellow and green. And what you can see is that you reduce the root mean square error for the 10-meter wind speed, especially over orography. So this is a domain over the Alps. And why you get this is quite visible here in these maps. So what you see in the global DT is you get some representativity errors for the wind speed because you're not completely resolving the orography. And if you go towards higher resolution, you start to resolve more of the details in the orography, and you get much less of these representativity errors. Then I also wanted to show a little bit about the runs that we're piloting that Christophe showed. So we have a visualization platform where we can also just do on-the-fly verification of extreme cases. So this is a case from 2 weeks ago, but you can do this for the cases we ran yesterday, basically. And this is showing temperature for a heat wave case over the Netherlands and Belgium over this 2 days. And you can see some verification of the 2-meter temperature over the 3 major cities in the domain, so the Amsterdam, Brussels, and Paris. Let's see.
Okay, so finally, the summary. Let's recap with this schematic table. So first of all, I will start with the added value that we have obtained with all the analysis of these case studies with the digital twin, global digital twin with 4 kilometers. versus the operational IFS with 9 kilometers. We can see that for mountainous areas, all the described here, all the detailed extreme events are improved. This is based on our experience with all the dozens of cases that we have evaluated. However, we still have some aspects that we want to test more or even improve. So for example, for extreme precipitation, convective and large scale, we still struggle to resolve it properly in the extreme events within flat areas. So some cases that gives like is the same value than the operational forecast. Some cases indicates that it's a slight degradation. So we have to invest more time in investigating these aspects.
And then for the on-demand, I mean, so we also see an improvement of extreme precipitation and wind speed. We see a bit less of an improvement for temperatures. That's basically because we're still working on proper initialization of the soil and the surface. But what we do see is an improvement in the spatial variability of low and high temperatures. So especially for urban areas or for mountainous terrain. And for medicanes and rapidly developing cyclones and squall lines, we only tested 1 or 2 cases, so we can't really say with certainty if we're adding value yet. So, yeah, thanks for your attention.
Thanks, Nathalie and Estibaliz. We have time for one quick question. If not, then we will, thanks again. We will move to the next speaker, Matthias Zeck, who will speak, whose presentation is towards the detection of energy critical situations in DestinE's Extremes Digital Twin.
Yeah, hello, my name is Matthias Zech. It's really a pleasure to present to all of you some results about this very exciting topic. So far we have heard very interesting results of the regional on-demand forecasting and when the triggering in this part plays a major role, and this talk will be about like when should we trigger, in order to detect situations, when in the past or in the current, when from an energy point of view, these situations matter, or when forecast errors actually hurt. So this is the idea of this talk about identification of extreme energy events caused by renewable energy forecast errors. So this is a joint work from me, Julia von Bremen, Marian Schröder-Homscheid, my colleagues from the German Aerospace Center, but of course also the full Extremes DT team with this slide with many names you have already seen now in 3 presentations. Yes, so how do we approach this problem? So one was that we tried to get engaged with key users. So one approach we took is that we talked to experts in this field, we made expert interviews with German DSOs, TSOs, and energy traders. Another one was that we had invented an interactive online survey where we could send to people and they could say for their own, this is an event which really hurt in the past. We also took a market perspective. So, of course, they're energy markets and they show lots of results, like energy prices and so on. And in this information, it's kind of reflected when something unexpected happened. So, one part of our work was to look at the market results. And finally, we will, in the future, we'll investigate energy system modeling tools where we make a simulation of the energy system and try to say, there it was critical, and also to use it for triggering. And I want to go a bit into these different blocks with you to show what we find out and where we're going to work on in the future. So the expert interviews were designed that we took we made conversations with different people and we asked for you what were the critical situations. So we found out different events in the past which really made some harm for them. We designed sort of like a diagram shown here on the right, where events can be either severe or frequent or both, to say events can be very often and heard, but also to identify like black swan events, which don't happen so often, but then if they happen, they can really hurt. And this is the result from a DSO in Germany, for example. He has lots of PV systems, and he said, for example, that fog is really an event where he says we need major improvements, and we made similar figures for all of the stakeholders we interviewed. This interactive online survey we programmed. So this is like a web tool where people can make on their own different weather events, as you can see there, and then they can drag and drop this event into this matrix. So in the end, we hope when we publish this, so this is programmed already, but we're waiting to publish it on the Destination Earth platform. We hope to get lots of different matrices like this, where we say, in this area, people say this event happens, and for me, it matters like that. So we're very, very curious to see how it looks like. So this market analysis is a bit more difficult, so now you should stay with me. So the idea of this market analysis was that, of course, in the prices, we have day-ahead prices and intraday prices, and they use different forecasts, so day-ahead forecasts and intraday forecasts. And this forecast update actually reflects, is also reflected in the prices. So like if something sudden happens, so there's like a forecast overestimation, the prices change. But there are also many other different reasons why price should change, actually. And the idea is like how to relate this. So how to filter out when the price spread was actually caused by renewable energy forecast errors. As you can imagine, there are other reasons. So like we tried to isolate the wind energy forecast errors, the solar energy forecast errors, and load forecast errors, and try to find their impact on the price spread, while also analyzing the effect of other reasons, meaning like, for example, the gas price, the CO2 price, or the day-ahead price. But also like, for example, if a gas turbine suddenly says that it doesn't work now anymore, but while yesterday it said it does, so you can expect that this has a huge effect on the price. So this should be modeled in a system, and we took as a method to model this, we took double machine learning, it's called. So it's one part of causal machine learning where you try to isolate this. And based on this, we could say this price, on this day, the price was mainly driven, for example, by solar energy forecast errors. I could even say by how much. I will not dig deep into this, but if you have questions, of course, you can come to me afterwards also. What you get out of this is then days like where you say there was, for example, a wind forecast overestimation or underestimation, and this has driven the prices by this amount. So here, for example, there's a forecast overestimation shown. So this has here led to a very large intraday price increase, as there was like a wind forecast overestimation. Another event happened when there was like a wind forecast underestimation, but still we didn't know like what caused this wind forecast underestimation. So we looked deeper into this event, and actually this was a fast running low event. And we also talked to stakeholders before from energy trading, and they said, yeah, these fast running low events, these actually are the worst. So we thought this would be a nice first case study to investigate whether we can improve like for this situation. And if we look at forecast errors during this day, where the fast running low was, we can actually see there was like a strong wind speed underestimation. But if we look at, for example, the wind speed APS spread, so what's in the ESMWF ensemble, like there was not so much spread visible for this day. And we thought this was quite interesting because like there was not so much uncertainty reflected in the forecast, but still there was a large error. So we thought about what could be other reasonable parameters for triggering, actually. So my colleague Lydia from Bremen is actually currently investigating whether, for example, the mean sea level pressure, the spread of it, can be used to say there's a more increased likelihood of fast-running low events to then potentially trigger a new on-demand regional forecast. And this is ongoing, but so far it looks promising that we can detect a high likelihood of fast-running low systems. Lastly, what will be in the future and what is currently now is what I said before, is the energy system modeling. So now we don't look at actually energy markets, but like simulations of it. And we as in our team, and Bruno Schiesker was first developing it. It was developing a ProPower system, it's called, where they use ECMWF ensembles inside energy system modeling. And we are currently trying to implement the ProPower EFI, we call it, so where we want to make on the day, putting all ECMWF ensembles inside to investigate whether there can be like something similar you meteorologists know from EFI, if you can use a power, like an electricity price EFI as a triggering point for future systems. This ProPower looks like this actually. So there's an energy system model, and you can derive, for example, probabilistic power flows. So it's mainly used for congestion management. So here you can see in this plot there are like different power flow simulations, and this is where it's currently being used. And in the future, we want to model this. We want to use it for the entire European domain, as shown here, that we can run it like permanently. To summarize, we made like we're currently and we analyzed different like tricky situations for energy markets, like based on user interviews, based on machine learning, and in the future we want to further look very deep into this triggering topic using situations, for example, as shown with the fast-running low event, where it's very hard to detect using heuristics, but also like using the ProPower EFI model as a prognostic model where we can say tomorrow is the day where it really matters from an energy system point of view. And if you have any questions, also I have a poster there in the end on the left there, so feel free to also come for deep discussions. Thank you.
Thanks, Matthias. We don't really have time for questions unless there is really burning one, but we will move to the next speaker. Thanks. So Kunyan from Delta-Res will present a global to local compound flood forecasting pilot service for Destination Earth.
Thank you very much. I'm Koen from Delta-Res, a Dutch Institute for Water Management Research. So today I'm going to talk about compound flood impact. We already see quite a lot of presentations about like extreme DT, on-demand DT. The question is how valuable, what is the added value if we bring that into compound flood forecasting, compound flood impact forecasting. I'm also going to dive a little bit into, let's say, how we bring this further from the demonstrators into pilot services. I'm also going to touch a bit about the so-called global to local concept, which matches the Destination Earth as a global digital twin. So the problem we're addressing is, really the compound events. So not only the precipitation, pluvial, fluvial type of flooding, but also in the urban delta, we're facing high tides, storm surge, wave overtopping. Especially all of those phenomena come together during extreme events like tropical cyclones. How do you understand the impact of those flood damages? So I'm talking about population, critical infrastructure, GDP in the area, et cetera, et cetera. So we're actually building a sort of framework, a technical modeling framework to bring all these processes together and try to understand the real damages. So this is already a project like 2 years ago. We built 5 use cases all around the world looking at different phenomena, high tides driven or storm surge or really the mountainous flash flooding areas, etc. It is quite successful. This is a quite technical slide, but we really showcase that for every single flood drivers, there is actually a model or two to address, to understand this process. And the next question is, how do you integrate all these models together in order to simulate the compound event? And of course, we also make use of extreme DT. That's the ultimate question we like to address, whether extreme DT with high resolution global data can lead to improved understanding of the coastal or the compound flooding. And we also make use of other global initiatives like GLOFAST for river discharges. We use our in-house global tidal surge model to understand the coastal storm surges. There is the wave model called HurryWave to quickly simulate ocean wave impact, but also the Sphinx model, which is super fast, flood inundation model to understand the flood extent. And last but not the least, the DelFiat, which is flood impact assessment, which bring the hazards together, overlay with vulnerability and exposure data to understand the flood impact. So this is also sort of a software modeling development which makes sure that we can simulate those events. But say, what is the main outcome of the previous demonstrators? So we're looking at all sorts of different events. Will high resolution WPs actually improve the flood impact simulation? I would say for most of the cases, yes, especially you look at extreme precipitation, in this case in the Humber River Basin, UK. The extreme DT really provide that high resolution information that allows you to quantitatively account for the precipitation. But of course, this really depends on the areas that you're looking at, the phenomena you're looking at, the large-scale wind that causes large-scale storm surge, for example, in the North Sea continental shelf. That does not necessarily lead to local improved storm surge. The same for the waves. So there is still a lot more work to be done. We need to do more validation with extreme events, including tropical cyclones. Uncertainty, there was a topic has been mentioned a lot, so including uncertainties is a key. Maybe we can make use of AI models to quickly simulate those impacts that allows more ensemble simulations such we can address uncertainties. Also, I think it's important to say that on the destination Earth, there is consistent wind, meteor, even wave data, but the coastal hydrodynamic data, meaning that tide and storm surge are currently lacking. So maybe there is also a demand to create such consistent information. And last but not least, we should convert those demonstrated into pilot services running for a period of time and just really to validate all the developments, whether that bring added value. So here comes the second part of my presentation, which is to look at how this global to local compound flood modeling framework can help understanding the impact. So under this new contract pilot service, we're developing 3 services. The core service is really looking at global storm surge tide currents forecasting. Will be a global model running operationally 24/7 for at least 1 year time and provide those information anywhere in the world. Second would be the downstream service. Downstream services make use of those information and try to improve the local forecasting. For example, the compound flood forecasting, we focus on Philippines in 3 different areas, and we move to also to a different industry, look at maritime impact of how global shipping routes can be optimized based on currents information, hopefully enhanced by extreme DT. So let me dive into this global tide and surge model, which is developed by Deltares. It is a global 2D hydrodynamic barotropic model that simulates a tidal propagation and storm surge interactions. There is no boundary condition because it's a global model. It has sort of high resolution, 2.5 kilometers for the whole entire world, up to 800 meters. Well, given the accuracy of the global bathymetry data, this is already quite good. The key process included to address tidal forcing, bottom friction dissipation, processes that become quite relevant in large scale like self-attraction and loading, also internal tides. Those are all included in the model. It is a global model, but actually has quite fast simulation speed thanks to the unstructured grid use and also the parallel computing. Of course, EuroHPC and a DestinE data lake will also help us to bring this performance to a different level. As you can see, the performance is actually already quite reasonable for a global model, but it is also keep improving. So this is really the key service that we're providing in this contract. Based on global tide and surge model, we're going to integrate such a model into an operational forecasting platform, then deploy this on the destination Earth data lake, running 24/7, and provide globally, but yet locally relevant storm surge, tide, and surface current forecast. And we will also develop a web viewer which allows user interaction and realization of this information. This will be developed as one of the services on Destination Service Platform, which will be since, well, next year, March 2026, will be online. And then maybe it's good to mention that all of these services are developed based on free software, open source software, which is based on Delft Fuse, Delft 3D FM as modeling software. You are encouraged to have a look at those free information. So here are some sort of underdeveloped glosses or global storm surge information viewers showcasing this information. We include variables like total water level, tide, surface currents. We include spatial varying information, looking at the lead time of 4 days, which is the lead time of extreme DT. And we also allow scalar time series realization, looking at really 10 minutes time step time series, which we include handcasts and also the forecast data. And yeah, we interpolate information on the fly. As you can see here, you can see the scalar time series, but also we import the global tide gauges as observation data, allows comparison or validation of our simulations. So this is wind data from NOAA-GFS, but we will, of course, also integrate Extremes DT, which allows visualization and some comparison. And information can be downloaded as scalar time series. You can realize that, you can download that. Possibly there could also be APIs to directly connect to these services. So I'm gonna quickly move to the downstream services. So based on this global information, this can provide very good boundary conditions for locally relevant storm surge and high tide forecasts. For example, in Philippines, where tropical cyclone is very relevant, there's a lot of TC-driven events due to high storm surges. So we will make use of global to local approach linked to the coastal boundary condition, but also the GLOFAS, which is the river boundary conditions. We expand to 3 different areas in the region and make use of the compound flood framework that I just introduced. We team up with NGOs like Red Cross to looking at how do you disseminate the early warning information into, let's say, the local task forces in Philippines that is executing the early warning response. Those are the user engagement. We have actually quite extensive user engagement sessions with all the local institutes, also including, for example, financial resource deployment institutes like START Network, Philippines Red Cross, Pagasa as a Met service who has a mandate in Philippines to disseminate or flood early warning. The last but not least, so I also mentioned maritime application. This is an entirely different sector, I understand, but this sector is extremely complex, but can actually benefit from the improved wind forecast, surface current forecast, as the global shipping routes optimization, or in terms of safety, but also reduce carbon emissions, saving fuels, arriving on time, etc., all benefit from extreme DT data and glosses forecasting. And last but not the least, but I think the interesting also to explore the commercial aspects of the entire program or services. This is my presentation. We also have a poster there, and if you have any questions, come speak to me and my colleague, Socorro, is sitting there. Thank you very much.
Thanks, Koen. Maybe in the interest of time, we will move to the next presentation given by Margit Kurka. So on Aladdin towards dynamic landslide risk modeling.
Well, good afternoon, everyone. I will be talking about Aladdin instead of Yannick, who couldn't make it today. So I will be going through his slides and guide you through our project. Aladdin stands for Assessment of Landslides Risk in Dynamic Environments. It started in January 2025, so we are kind of at the beginning of the project. And it's a consortium of interdisciplinary experts, including remote sensing experts, IT experts, AI experts, geographers, geologists, and civil engineers. What is the problem? Landslides cause a lot of damage globally, and especially Europe is concerned with landslides. And here in Austria, we have a lot of landslides occurring. There are a lot of economic losses, and there are also fatalities in connection with landslides. And most of the damages we have with landslides are related to rainfall-induced landslides. And the idea behind the project is to provide a short-term prediction of what's happening if, for example, a storm is moving in, if an event is coming into a region, and to kind of give the decision-making people a tool to say certain slopes are more prone to landslides during that event than other slopes. Our project area is in the southeast of Austria. You see two maps here. You see entire of Austria, where there are a lot of landslides, from an inventory, a lot of landslides put in the upper map. This is not complete at all. Our project area is in the southeast of the state of Styria. And you can see it's mostly red, so it's very susceptible to landslides. It's prone to landslides from the onstart. And we have a huge inventory database for that area. We have thousands of landslides mapped there, which are also connected to rainfall events, which is very important for the calibration and the verification of models. Now, globally and also nationally and also on the state level, we have a lot of hazard maps being developed over the last decades. And that's mostly due to remote sensing, because we can't have regional hazard maps and provide them to the decision makers. Those are most of the time static. That means they are made at a certain point of time, and at that point of time, that's how it is. So they are given to the decision makers. If 10 years passed, it's still the status quo from 10 years past. The idea about the Aladdin project is to put some dynamic parameters into these hazard maps, meaning to put weather forecast, dynamic weather developments, but also land use changes, land cover changes into the susceptibility mapping of landslide, and therefore have a better tool to make decisions, especially in disaster events. What goes into landslide susceptibility maps? Underground information, geomorphology, topography, land use, landslide inventory data from past landslides to calibrate and verify the models, infrastructure, and what should go in there now in the Aladdin project is land use change, for example, deforestation or windfall of trees, and also precipitation predictions from the, for example, extremes DT data, which we're looking at. But also antecedent rainfall, meaning a priori rainfall, where we have a soil saturation. For example, if we already have a long enduring rainfall, which already goes on for a few days, we already have a saturation in the soil, which means if I have an extreme rainfall following, the slopes are more prone to fail. The methods, I will not go into everything, just the first point. What we are right now doing is we're doing a comparative analysis of the extremes data with local weather station data to see how well we can integrate it into a landslide susceptibility model. What we have been working with is the global DD data at a 4.4 kilometer resolution. We also have been provided with a 2.4 kilometer resolution data from ECMWF, thank you, and also with historic data of an event where we have about 3,000 landslides which can be linked to that event and which we're using to calibrate our model. Some of the results, of the preliminary results we have at the moment, is that if we have accumulated rainfall, like 3-5 days of accumulated rainfall that we have, for us, for our purposes of landslide modeling, relative good correlation between the ExtremeCD model and the local weather stations. So it's in discussion now within the team if we will use that for the soil moisture data that will go into the landslide susceptibility modeling. The comparison of the data with the local data showed that on an hourly basis we had very poor correlation. On a daily basis the correlation was very well. I will show that in the next slide. Something we already heard is that convective precipitation events in the summer are often not captured, or they're not captured well enough. But although, as I already said, although the hourly prediction is poor, the daily prediction is, for our purposes, looks very well, and the correlation is 0.86. What we also could see is that dry periods are detected very well. Normal rainfall is normally overestimated in our area, and extreme events are often underestimated. We also compared the 4.4 kilometer resolution data with the 2.8 kilometer resolution data, and it showed a slightly higher accuracy. So it would be really nice to, at some point, also have the 500 regional data to just see what the differences are and to see how well that could be integrated in such a model. So our first conclusions, I already covered some of them. We have a pretty good agreement of the 4.4 kilometer data with the station data on a daily basis, not on an hourly basis. It does not capture some of these extreme events, so we have to look into that a little bit more. And we seem to have, like, the cumulative rainfall we have is also in well correlation with what we need. Our recommendations is that in some cases the historical data is really, really important to calibrate our models, to see if it works for the models, if we can actually roll it out, and also to have higher resolution data in case of the landslide susceptibility modeling. I don't know if I'm in time. Then our next steps. At the moment, we're discussing how we're going to use ExtremeCD data in our susceptibility modeling of the landslides. Most likely it will be the daily data and accumulated data. That is still in discussion, how and what we're going to use. We also want to integrate other data like land use data, land use change data in the model to have that dynamic component in there. And at the end of the project, which is like a year and a half ahead, there should be a user interface where we can visualize this dynamic hazard map, where a user can go in and just click on it and see on a daily basis, have a prototype where on a daily basis we can make predictions which areas are more landslide prone than others. And then, of course, in the long future, we're looking at the rollout nationally and internationally, how that can be accomplished. And with that, I end my presentation, and thank you for being here.
Thanks, Margit. And our final speaker is Nathalie Toyes, who will present Urban Air, a new digital twin to support climate adaptation in cities.
Right.
Okay, so you're not seeing double. I already presented, but now I'm putting on a different hat. I would like to talk to you a little bit about a Horizon project that we just started called Urban Air. And this is to create a new digital twin to support climate adaptation in cities. So we are funded by this Horizon call for new digital twins to go into Destination Earth. And we're just a few months into the project, so all I will present to you is beautiful dreams and wishes and hopes. So yeah, we'll see how it turns out in 3 to 4 years. Okay. So the aim of Urban Air is to urban simulations for air quality and heat resilient strategies. And we do this along 3 main pillars. So one of the pillars is climate adaptation, so answering questions of users related to where should I put my green space? Should I go for high-rise buildings or build low-rise, more urban sprawl buildings? And then the second pillar is related to urban planning and design. So this is related to wind comfort. How do you design your recreational spaces? What are the mobility choices? That we have, the options that we have. And the last one is related to hazards response, and this could be related to weather and air quality extremes, such as wind extremes. So there's a windstorm coming. Or heat extremes, heat waves, or also air quality extremes. And we're building up on the Destination Earth platform and going through a range of modeling approaches that I will show a bit later. So the consortium, I mean, we're a nice mix of interdisciplinary people. So we're going from computational scientists, environmental modelers, to behavioral modelers, social scientists, and communications experts, etc. So we have to do a lot of talking to each other to start to speak the same language. So we're organizing many live meetings so far. We've had 2, and a lot of discussions. So we're building on existing tools and technologies and hoping to connect to the Destination Earth infrastructure. So the way that we want to answer questions related to these 3 pillars, we use a variety of different models. And it depends on the question which of these models that we use. So we have in our large toolbox, we have physical models, so ranging from the regional scale models that, for example, Christoph presented, towards really street scale, large eddy simulations, so very accurate representation of the atmosphere. Which, I mean, so we have urban climate models that are might be a bit less accurate and a bit less detailed, but they run fast. But we also have these large eddy simulation models that really resolve all the turbulence. They're very accurate, but they take a long time to run. So depending on the question, we can click, and we hope to click which model you can use. Then for the uncertainty quantifications, we mentioned many times, so we have 3 methods that we want to use. So these are emulators. So to emulate these accurate models, so we can do multiple fast simulations. There are data fusion and super resolution, so fusing mostly satellite data, but also air quality observations, and data simulation. So, and then from the social scientists to actually engage with the users a bit more, we have behavioral models mostly based on agent-based modeling. So for short-term decision-making, so related to an extreme event, but also long-term, like climate adaptation scenarios, how are these going to be taken up by the users? And decision support tools to help them. So to demonstrate this, I just want to take you to an example user journey. So pretend I'm a user, an urban planner or a municipality at the municipality of Antwerp in Belgium, which is one of our pilot cities. And And I want to have a future-proof city with the least mortality. I'm asking the question, what kind of interventions can I make in the city to prepare for current and future extreme heat wave events? So what I finally want as a user is some sort of scorecard, and this is just an example, you don't have to read it, some kind of scorecard that rates different nature-based solutions in this case. So different adaptation scenarios, how these are rated. So then we go through our nice modeling chain. What do we need for that? We need some behavioral modeling to come up with the solutions that will be attractive for the public. And then these will be fed, these will be fed by the street scale modeling, so really high resolution, super high resolution modeling of thermal comfort. And this needs to be fed by the city scale modeling. And then comes the regional scale modeling and the global scale modeling in Destination Earth. That's already ongoing in Destination Earth. So we're building up on that and going towards more higher resolution targeted simulations. So if you have this modeling chain, you can also do some scenarios. So, I mean, for the regional scale, these can be the famous storylines. What happens if this extreme heat wave event happens in the future climate? But also you can think of city scale interventions like massive scale greening or street scale, whoops, I keep clicking forward. Or street scale interventions like planting one tree here. I mean, that's kind of the level you can get at with these types of models. So, I mean, like I said, we build on this cascade of modeling. So we use both the extremes DT and the climate DT, depending on the problem. And then we cascade down in the resolution, so higher resolution. So we go to the regional, we go to the city scale modeling, and we go towards the really street scale. So step one, going through this. So this is just an example case. So we grab some data for using Polytope, a nice tool. It's been mentioned many times already, and I assume that Thiago will say something about this tomorrow. And then we grab a regional heat wave case. So this is a case in 2018 over Antwerp. So this is the 2-meter temperature. Then we can downscale using a city scale model. So this plot here shows the urban fraction of Antwerp and surroundings and the resulting 2-meter temperature if you feed this really high resolution urban data in there. Then we can use these simulations to go even further. So these are simulations done for just a small part of because they're really, really high resolution, so sub-meter scale, meter to sub-meter scale. And this is for a part of Antwerp. And you can see that you get really detailed maps of, this is radiation, we have wind speed and temperature. And you can get very detailed maps of thermal comfort at the street scale. So then we use this, and plus the scenarios that we create, to run through agent-based modeling to see which nature-based solutions we can have the best benefit. So this is just showing an example of what we hope to do and some real simulations that we've done already. But in the future, we want to work out more of these types of user journeys. We have to work out the science and the technology for this further. So yeah, ask us again in 2 or 4 years and see where we are. So to be continued, thanks.
Thanks, Nathalie. So we have now 10-15 minutes of discussion. So you have the possibility, if you are online, to ask questions on Slido. We can also take questions from the room. But to maybe steer the discussion, I have also prepared some questions for the speakers. You're also invited in the audience to give your perspective on those questions. And the first one would be how the Extremes DT could be a game changer. And what is the most important feature of the Extremes DT, which enables possibilities which were not possible before for your application. So would anyone share their thoughts on that? Otherwise, can I ask some speakers what would be their most important feature in the Extremes DT? Christophe?
Yes, I can give some words. I mean, yeah, talking now from the perspective as a developer of weather models, working in this area for quite some time already, almost 20 years now. So the most important part for me is really that, I mean, of course, everybody's talking about resolution. Resolution is really high, and it is the twins are running on higher resolution than what we have so far in operations. But this possibility on one hand side to have it configurable, very flexible over any area in Europe, this is really a game changer for us, because we are used as at a Met service to run our model on static domains, always on the same place, very, let's say, unflexible. So this is really game changing for us. And in addition to that, this connection to the impact sectors. I mean, we were always working together with impact sector developers, but especially within this Destination Earth initiative, this is much stronger than it's before. So this co-designing of workflows from the beginning of the development is really, I think, something very special and a game-changing things, opening really a lot of perspectives for the future, I think. Yeah. So.
Thanks, Christophe. Anyone else? Can I have maybe the perspective of an application user?
Yeah, I think for us it was game-changing to just have the data and to work with it and to see, you know, how well it works. And I think in the course of the project, it's going to be game-changing to see how well maybe the better resolution data works, how well the 4.4 data works, and if it can be used for susceptibility mapping. And just that it's available is a great thing, period.
So you need the data for validation, if I understand well, in this stage of the project.
Just to have data and also historical data where you can actually develop a model that's validated, that's verified, and that works well.
I think you also made in your presentation the point that you needed to go back to certain time periods where you had reference data to and have that data set available, which is, you know, requires, of course, you know, being able to shift that simulation case.
Kun?
I can say something from here. I think our impact sector will look at flooding. I think what is really important is that, of course, increased resolution, accuracy, those definitely help for your flood modeling. But say if you focus on any local region, you also need boundary conditions for your impact-based model to be able to perform. So with a globally consistent weather forecast, improve accuracy, then you can have globally applicable impact models. And then you can zoom into any local areas and improve the prediction, which is very powerful, in my opinion.
So consistent data at the global scale.
Exactly.
Thanks. Esti?
Yeah, I just wanted to say that for me, it's not only, as Christophe said, that it's not only the resolution, it's the whole workflow that we have created in the Extremes DT. Because the on-demand or the regional DT runs from the global DT. So first you have to develop the global DT, then it takes advantage of this high resolution, then it runs in a tailored decide area after an automatic triggering mechanism in a specific area, and then it goes to the impact sector. I think that all this added value without DestinE, it could have not been possible because it's an investment of effort and progress in terms of modeling that we couldn't do it just in a normal project. So I think that this is the whole added value.
There is a question on Slido.
Thanks, Esti.
For Margit, have you considered virtual or augmented reality to visualize the urban solutions to complement your Excel scorecard to allow your users to take a tour of the installations that you would recommend?
Natalie.
You want to take that?
Not necessarily, but I think we're still working out how to visualize it properly. No. But we're currently talking to a lot of users in the pilot cities, so that's Antwerp and Barcelona, to see what they actually want. So, yeah. Thanks.
Thank you. We have a question at the back.
Thank you. You mentioned, I think it was in your presentation, about wildfires. Do you also plan to do that on this on demand? Because my question is more on how, I mean, this is something that your global DT will not see. You cannot foresee the occurrence of a wildfire from the global DT as opposed to flooding or other things.
I think that's for Christoph.
Okay. So in the case of wildfire, I wonder who pulls the trigger to launch the on-demand, which is something that you cannot foresee from the global run.
Maybe I missed the beginning, yes, but wildfire is part of our project. So we also are piloting cases, wildfire cases, and so this is treated within our workflow, in what we pilot at the moment. Yes.
Yeah, my question is how you want to automate this.
Automate this.
Yeah.
Well, that's a very good question. Yes, and I think at the current stage, this automatic is not yet really answered.
I mean, one, I think. My point is, it's something that you cannot foresee from the global one. So there must be someone with, let's say.
Yeah, you would base it then on risk assessment based on history and but
in operations. No, I mean,
way,
how do you automate this in operations?
By now, I don't have an answer for that.
Okay.
Yeah.
That's fair. Thank you.
Okay, thanks, Christoph. I think Irina would like to take the next question. Do you envision self-service extremes DT simulations to be available to regular DestinE platform users?
Yeah, actually, I take the two. So this is something we are discussing also with the European Commission and also with the national Met services, who are the mandated institutions for extreme events. So it's not something that will be self-service. You always need an expert in the room, and it's also because of the protection of life and properties, because the national Met services are the ones who have the authority to issue warnings. So even if, so basically this is the data access and how this is going to work, it's an ongoing discussion. So, but one thing I can say is not a self-service that anybody can run the 500 meters. First of all, because this is an expensive tool, not the computational resources wouldn't allow it, but also second of all, because for present day cases, of course, it's a question of mandates and who issues the warning, so that needs to be respected, and that's the roles of the national Met services, who work with the various institutions. But there are ongoing discussions, but I think that's what we can say so far. Was there anything there? But then, of course, data for past cases would be made available once we manage to run on the Euro HPC. That will be available for the platform. And then for these what-if scenarios, if somebody has an idea of one what-if scenario for an extreme in a future climate or a past extreme, you would like to explore something, this is something which the idea is to make it more broadly available. But for present day, the idea is to complement basically what the Met services have already.
There are two further questions now. One for Matthias about the statistics. how often errors came from forecasts and how often they came from the other factors that you mentioned?
Yes, so far I cannot actually, but it's in the data. So I haven't focused on this question completely because I was more interested in situations when it was caused by forecast errors. But I think this would be an interesting statistics to further analyze. So I think what Gerd Heilscher means not the forecast is, with error is mean like the price spread, I think. So the price updates, but I think this answers the question. Hope so.
Thank you. And maybe we will take the final one from Slido. I don't see any further hands up in the room. We're at the end of the time anyway. So, but the one, I'm not quite sure who this addresses. If we already have studies linking a risk range to the alert levels defined by the regulation enforced with target regions.
Christoph, maybe?
Well, no, the answer is no, not yet. So I would say, I mean, the local regulations, of course, yeah, very local. What we have in place, I said, we have the semi-automatic way of running, which means we have the suggestions coming out from the automatic detection and triggering, but plus this is done, and then there is a team, let's say, deciding what to do, and they take into account, for example, meteor alarm information. So meteor alarm is this European initiative gathering all the warnings for Europe together on a place. So this is taken into account. So people, and these warnings are already based on local, let's say, conditions. So this is an indirect way as it is done now, but in general, no, there is no direct study at the moment on. Yeah.
Thank you.
Thanks a lot. Well, maybe it's time to draw the session to a close. Thanks again to all the speakers and for the interesting questions at the end. So next session is on the climate DT. What time do we reconvene?
Yeah, we have half an hour break, I believe.
Half an hour break, okay.
4:15, okay.